you. Okay, hi everyone. I'm Jonas. I'm gonna share this presentation with my colleague Eric, as it has been said. Eric and I are working at the Cantonal Statistical Office of Neuchâtel, and we are pleased to share a piece of our work with you in this talk. Today, we decide to present a public statistics specific use case we perform in R. It is not about R in itself, but more about how R is helping us in our job. So the presentation will be in two parts. The first is about the dirty part of the job, if I may say, cleaning and modeling the data. And the second part will be presented by Eric and is about the analysis itself. So the content will be the context in which this work takes place, the data, what data are we talking about, data processing, how to make the data meet our analysis needs, and the second part.
Interrupt you, Jonas. Are you sharing your screen?
Sorry, you don't see?
Share it because we only see you.
Oh.
We don't see your slides.
Okay. Oh, sorry. Here. It's okay?
Okay, perfect. Thank you.
Okay, sorry. I'll keep going. Oh. Okay. Yeah, this is about the content. I just explained the context, the data processing, and the second part will be presented by Eric. The context, part of our job as a statistical state office is to propose solutions to evaluate the relevance of public policy, and often evaluating policy requires longitudinal analysis. Usually there's a before and after event period, and we try to measure the impact of event by comparing both periods. But in our case, there is no real before and after period, but there are a number of public benefits that occur at different points of time in the people's life. And they could have an influence on several outcomes. In this context, we think it's interesting to apply a sequence analysis in which the analysis focus point is the whole period, without the prior knowledge of what could be the potential breakpoints. The basic idea is that in the young life course, some services are made to help the labor market integration. And we believe that studying life course through the different services could help us to understand the success path and highlight the improvement we could make in one or another service. But first of all, I'm gonna talk about how to deal with administrative data, which are usually not made for statistical purpose. So just a word about the data. We dispose of the registries of public offices, such as the employment office, social assistance, schools, training, and so on. They contain the record of the services offered to the population, with the start and the end date of the given service. Based on this data set, we can build life courses of individuals as long as we can identify them across the different registers. So that's the difficult point. The sequence analysis needs the data to fit some requirement, and I'm gonna present the three different steps to transform the data. Firstly, as I said, administrative data isn't made for statistics, so we have some registers with personal ID that is helpful to identify the individual, and other registers miss some data and the ID key identifiers. So how to merge data sets that miss key ID? Our idea here is to use a third-party dataset, population census, and perform approximate matching with socio-demographic variables such as names and surnames and date of birth. Okay. So the first part will be about approximate matching. There's a package in CRAN that meets our needs, record linkage. It is useful to join dataset on approximate matching, and we'll see in the next step how to do that. It includes a good feature, and I'll let you go through the package feature if you want. I will just show you one application. So the first transformation is to split the names into different fields. So for instance, James, Amon, Edward would be split into 3 different fields in the datasets to be compared. The underlying idea is that by splitting the names and surname in several fields, we reduce the impact of missing second or third names when it comes to measure the between string distance. I will show you what I mean by between string distance in the next slide. After we bind all the registers together, so we get the census here, the population census with truthful data and the key ID. I mean, yeah. And on the other data frame, we have the individual we are interested in, but with sometimes misspelled name. For example, Rachel here is correct in the census, but misspelled in the other different. But we are trying to match together. The next step is to build all possible pairs. Each row is paired with each other. That lead to a data explosion, as the output will has now n time n-1/2 rows. There's a mistake here. There's only one actually. That could be an issue, but there is a way to deal with it with the blocking method. In our specific case, we force a match between the date of birth. Actually, this sensitivity this reduces a lot the data size. Actually, to perform the string comparison, we decide to apply the Levenstein distance algorithm, which is defined as the number of single character edits needed to change a word into another. For instance, here we will compare John with John and compute the distance between those 2 fields. In each pair, we will compute the distance. We are almost done. It's time to weight the pairs. The weight is an indication of how likely a pair identifies a true match. It is closely related to the distance we compute, but it's not the only thing in weight. Actually, it is also related to the frequency of an observed value. For instance, John, which will be observed a lot of time, will get a lower weight as because it is a common name. But another name, like for instance, Archibald, will be less, with a better match, will get a higher value of weight because it's less observed in the data set. So for instance, here we have our rate compute for each rows, which pairs. And as you can see here, John, Damon, Stephen, Doe is exactly the same, but get only a 0.83 instead of 1 because John can be observed several times. The final step is to identify the true matches. So we'll the package propose different weight method and also different way to to classify the pairs, but we decide, because in our specific case, it's not a big deal if we lose some true matches or if we accept some false. So we have only performed a simple visual inspection, and as long as we can identify the match visually, this one should be this one, we decide that it's a true match. And all observation with above this weight threshold will be considered as false matches. We'll only keep the observation above this threshold that still identify good matches. So, and now once the registers are cleaned, we can consolidate all the data. So we have all the registers here with all the clean data that we find by approximate matching. And we will perform two different data modeling. The first is we record all the service code using binary codes. That will be useful in the next steps. We will see why. And the second transformation is that we transform the service period into the individual age. That is for two reasons. Firstly, because in our sense, the happening date of an event is not as interesting as when it occurs with respect to the individual lifetime. And secondly, it makes more sense when it comes to comparing individual born at different time. So for instance, here is the difference between those two dates in years. And now we just have to build the sequences. So in our case, the period of interest is a 10 years period between the age of 15, post-mandatory school, and the age of 25, where most of people are subject to be in a professional position. We decide to split this period in months. We then build sequences of 120 time points, and by observing whether the individual was in the service at this time. For instance, here for Rachel, she was on this service at the age of 15 and 1 month. We can notice that for this individual, for instance, Rachel, was in this service at this time and in another service at the same time. So that's why the binary code are useful, because we only have to sum up to get a single line per individual. So now we can see that, for instance, this person was in several services at the same time by only sum up and keeping one single row per person. If you observe all the values of the data set, for instance, it gives us the alphabet of possibilities. There is another mistake here. It's only 2 to the power n possible combinations. Eric will now show you how the alphabet size could be an issue in the rest of the analysis. Thank you. Can we maybe switch to the Eric? Oh, I have to stop sharing my screen, I think. Yeah. Eric?
Yes, hi everyone. Can you see my screen?
Yes, we can see it. Thank you.
Great. So hi everyone, my name is Eric Röthlisberger, and I'll do the second part of the presentation. So once the data has been structured correctly, it is now possible to move on to the analysis phase and the production of graphs. And for this, we use the TraMiner package. TraMiner is very easy to use. The difficulty lies more in the data preparation and graph interpretation. So in this diagram, I'll show you the typical step of a sequence analysis very shortly, and then we'll come back into details in every steps. So the first step here is what my colleague Jonas just presented to you. It consists of collecting, integrating, structuring, and preparing the data. The next step is alphabet reduction. I will show you on the next slide. And then we will produce the first graph, the standard graph in the sequence analysis. Those are very typical graphs. And then we will compute a distance between each live courses. We call these live courses sequences. And this will give us a distance matrix. And from this distance matrix, we will graph a dendrogram, which looks like a tree. And then at the end of it, we'll choose an ideal number of cluster, which will give us, again, the same graph, but for each subpopulation. And this will help us to interpret the data. So the alphabet reduction. In sequence analysis, the theoretical framework specifies that one should not exceed 12 states. Because with more than 12 states, the graphs are too difficult to interpret. And with real data, I can assure you that you can get more often 12 states. 12 states is very limited. So most of the time you have more than 12 states. So you have to reduce the alphabet of the states. And to reduce it, to reduce the number of states, we use two different logics from which we derive rules adapted to the data set. So the first logic is the frequency of the situation in all sequences. The situation is called the states, if you want. So one rule could be all states occurring less than 2% of the time can be regrouped in a state called other. By doing this, we will reduce the alphabet. The second logic is create priority rules when several states appear at the same time. For example, when state X, state Y, and state Z appear together at the same time, it becomes state Y. With the following domain rule, state Y has priority over state X, which has priority over state Z. Editing these domain rules need a thorough knowledge of the area, and you also need to keep in mind the purpose of the analysis when establishing your state hierarchy. So this task cannot be delegated. You have to build those rules, those priority rules, with the domain experts. This is very important. This is not only a statistical matter. So in our case, we had to go from 56 states to 12 states. You can see them on the gray line. On the gray line are the real states. So that's the reality. On the white line, you can see the frequency for each state here. It's sorted in descending order. And on the colored line, you can see the 12 states, and below you can see the priority rules when they are applied. For example, here and here or here. And we have greatly reduced the number of states by classifying in other the states that rarely appear. Yes, you can see here because it's sorted in descending order. Those are states that appear very rarely, only 8 times, and all of these situations we put them together in a category called other. By doing this, we can reduce the alphabet. So how to interpret a sequence? You have to remember that a sequence in our data set is a row, but columns, and this is something it took me a long time to really understand, columns are not variables. They represent time points. In our case, age point. For example, 15 years and 1 month, 15 years and 2 months, and so forth. And the sequence expresses 3 dimensions, which are scheduling, temporality, and duration. Scheduling is the order in which the states appear. The temporality is when the states appear on the timeline, and the duration is the number of occurrence of a state in the sequence. So how to graph a sequence? We use color to represent the states. To make a good graph, you need to choose color carefully. This is very important because if you don't choose the color carefully, you won't see anything. Your graph will not be understandable. For example, state appearing rarely must be given a dark color to make sure you don't miss them. You don't miss them in the graph. You can change the state color very easily. I show you here the R code to change your color. This is, for example, indigo color. And it's easy to change, but you have to do that very carefully. So now the first standard graph in sequence analysis is the index plot, which shows all sequences. If you have a lot of data, which is most of the time the case, the graph can be very messy and difficult to interpret. To make it easier to understand, it's a good idea to sort the sequences either from the beginning or from the end of the timeline. So how does it look like? It looks like this. So this is called an index plot, sorted from the start. So the states are sorted from the start of the timeline here. So on the horizontal line, it's the timeline. Unfortunately, I don't have the time to interpret these real sequences, but what I can tell you, if you show this type of graph to the domain experts, they will quickly see interesting elements. So, and this one is the same graph, but sorted from the end. And it's sometimes interesting to sort it from the beginning or from the end. So here, the second standard graph in sequence analysis is the chronogram, which focuses more on temporality. It's easier to understand it, and it's the favorite graph when you start an analysis, but it can be misleading because colored areas do not represent entire sequences, but state frequencies at each point of the timeline. So how does it look like? It looks like this. So it's here you can see the importance of each state, and especially which one appeared on the timeline. For example, here you can see that there is a very dramatic drop of these states, and this is caused by administrative decision, for example. This is the financial benefits which are by administrative decision stopped when the people reach the age of 20 years old. So now we are going to the next phase, which is called the sequence aggregation. So why do we do that? To reduce complexity, which will help us to understand and explain reality. And hopefully this understanding will help us and help the public policymaker to make good decisions. On the next slides, I'll show you how to integrate sequences. In other words, how to put together similar sequences and similar life courses. To aggregate, we need to measure a distance between sequences. This distance must take into account the three dimensions: scheduling, temporality, and duration. And there are different distances in the traminer packages. So I'll show you in a toy example, how does it look like to compute a distance. A distance between two sequences. To transform one sequence to the other, we need to make a number of operations. It can be a substitution, an insertion when there is missing data, for example, or a deletion. For example, here the cost is a substitution. To go from this state to this state, it's a substitution because it's not the same state and it costs 2. And here it's the same, it's equivalent, 0. Here it's an insertion, 1. Here it's a deletion, it costs 1. And the total of those costs makes the distance between the two sequences. To continue with our toy example, this is what you get after measuring all the distances between all the sequences. This is called a distance matrix or a dissimilarity matrix. So let's go back to our case with our real data. The best choice in our case was the optimal matching of transition sequences distance. You can see the output to compute the distance matrix. It's very easy to use. For this distance, we need the transition rate matrix. You can see it in the formula for the substitution cost that you need the transition rate. So what is a transition rate? This is the computed probability for one state to switch to another state on the next point on the timeline. Here you can see that the highest probability are for a state to remain in the same state the next point. For example, here, this is the same state here, and for example, here also. And for example, RCP, which is a state here, has a very, very high probability, 0.98, to remain RCP on the next point. So now we have our dissimilarity matrix. We can aggregate sequences with the Ward method from the cluster library. So this is the cluster library, and this is the algorithm Agnes, and this is our distance matrix. And and show the aggregation result in a dendrogram, which looks like a decision tree, but it's not. It's a dendrogram. It grows from the leaves to the trunk by aggregating sequences by proximity. The dendrogram is very useful to choose the ideal number of clusters. In our case, it seemed obvious to choose 4 clusters. I'll show you how it looks like. So it grows from the bottom to the top. So here at the bottom, you have all the sequences. And what the algorithm do is it put together similar sequences together, and then it makes a cluster by proximity. And here in our case, we choose 4 clusters, which is a good choice between too many clusters and too few clusters, which is 1, 2, 3, and 4. So once you have the cluster, you can graph index plot and chronogram again, but this time for each cluster individually. And with the help of the domain expert, this graph will help you to understand reality and describe the subpopulation discovered by the cluster. So here is, for example, the cluster. So you can, what you see is index plots exactly as before, but now it's separated for each cluster. And now the interesting part is that you can very quickly see that those represent subpopulation very, very different. You can see only by looking at the color that here the yellow is very dominant, here the blue is very dominant, and here this sand color is very dominant, and here green color is very dominant. And when you know the signification of all those states, you can very well interpret what does it mean. And this is only because this is thanks to the sequence analysis. And here you have the same thing, but it's again the chronogram. And after getting the habit of using those graphs, at least it's my case, you prefer the index plots. At the beginning, it looks like very messy, but at the end of it, when you know that your data, it's more interesting to see the index plots. And here I reproduce the process of the entire analysis part of the sequences analysis. So this is the end of our presentation. I don't know, maybe you have any questions?
So thank you very much, Jonas and Eric. I'm afraid we don't have questions, time for questions right now. But as you know, after the last presentation, there will be rooms, and there will be we will be able to actually discuss with all the speakers in the different rooms. So thank you again for your presentation, and we move to the last presentation before the break.